All right. So that's the difference between those four things. But you could see that they're intimately interconnected. But there's actually also a different way of looking at it. You could also picture the same table as a tree diagram. And so this is just another way for us to be able to really picture conditional probability. So it doesn't really matter which one you choose first, which variable you choose first, whether gender or computer ownership. I'll just start with gender. So I'm going to put gender here, and then I'm going to put computer here. And then at the end, I'm going to talk about what is the actual event, what's that combination called. And this should look sort of familiar from some of the probability space stuff we've looked at before. So first, we need to know, okay, what is the probability of being a male? And what's the probability of being a female in this universe? Well, in this universe, the probability of being a male, you could find down here, is 1,500 out of 2,000. And so the probability of being a male is 75%. On the flip side, the probability of being female is 25%. And together, this makes a total of 100%, right? Notice that these are not yet conditional probabilities. They're just regular old probabilities. We already know how to do this. But if we knew that they were a male, if we already knew this person is a male, then how would we figure out if they own a laptop or a desktop, right? So what is the probability that they own a desktop, given that we already know that they're a male? Here, we compute conditional probabilities. So given that we already know that they're a male, what is the probability that they own a desktop? So here, we want to reduce our world to just the male world now. There's our male world. It's a man's world, right? And so what's the probability that they own a desktop? Well, that's 33%, so 500 out of 1,500, right? Repeating, right? So here we find that this is our new world. We're not using this 2,000 number anymore. We're using this smaller space, just the male space. Now, what's the probability that they own a laptop given that they're a male? Well, these two should add up to 1. And indeed it does. It's 1,000 out of 1,500. So that's 0.6 repeating. Just to make it shorter. All right. And now we have here we have, at the end of this, we know that they are male and they own a desktop. And here we know that they're male and they own a laptop. You have to, right? Because it's like you follow this little tree, you follow that little tree, right? Now let's talk about females. So given that you know that they're a female, now we're talking about this universe, right? Given that you know that they're a female, what's the probability that they own a desktop? So desktop given female. So this is my new universe, and it's out of 500, right? And we have 100 out of 500 students owning a desktop, and so that's 20%. Don't need that zero. And what is the probability that they own a laptop given that they're a female? Well, these two should add up to 100%, so it should be 80%. And so it's 400 divided by 500, and so that's 4/5, 80%, right? And so here we know that once you go through this tree, like this branch, right, this path, we know that you're female and own a desktop. And here we know that you're female and you own a laptop, right? All right. So by the end of this, you get these 4 different events. But these 4 different events have very different probabilities. It's not like before heads or tails where we could just all assign them the same probability. But not only that, but if we look down deeper, we know that these are different than these, right? Because these are all out of the total number of students, but this is out of whatever condition is being met. I'll put this in black. Right? So how do we find the probability of mail and desktop? But now it's not a conditional probability. I just want to know this number. How do we find that? Well, if you had this entire table, it's actually quite easy, because you would look at mail and desktop, 500, out of 2,000, because it's out of the whole world. It's not a conditional probability. So that's 25%, right? And what is the probability of mail and laptop, right? Well, you would look at this one out of 2,000, so that's 50%. Notice that these two don't add up to 100%. You actually have to count all 4 of these in order to add up to 100%. So what is the probability of female and owning a desktop? That's 100 out of 2,000. So that's going to be, I think, 1 out of 20. So that's 5%. And what is the probability of female and laptop? So that's 4 out of 20. So that's 4 out of 20 to 20%. I just blanked out for a second. All right. So here, what we see is when you add all of these up, then you get 100%, because this indeed is the entire space. 25 plus 50 plus 25, you get 100%. And additionally here, you add these up, you get 100%, because these are all like subspaces of the universe. But this one is out of the whole universe. You get 100%. So that's how it breaks down. Notice that these are all different. That these probability of desktop given mail is not the same as the probability of mail and desktop. This one is out of the entire universe. This one is out of this limited universe of already knowing that they're a male. Okay, so that's the tree diagram. So these are going to be the same numbers. I just rewrote them in a nice, clean, computerized sort of way. Right? So here's my world where you know that they're male. Here's my world where you know that they're female, right? These conditions. This adds up to 1. This adds up to 1, right? But here's the thing. What is the relationship between these events and these guys, right? Because here, when we come to events, we're really talking about the probability of D and M, and the probability of laptop and mail, right? Is there a relationship between conditional probability and probabilities? Well, actually there is, because if we remember what this was, the probability of desktop and mail was 500 out of 2,000, right? Let's look at that relationship. Well, here we're really putting together the probability of that little overlap space over 2,000. That is different than this one, which is 0.33. And that's also different from this one, which is 0.75. But here's what I want you to see. Let's play around with these. If you multiply these two together, let's look. 0.75, we're really taking 1/3 of 75, right? But I'll just multiply it like this. Just put as many as you can. Basically, you get about 25%, right? And that's that, right? And let's see if that rule seems to work for every single one of these. the way that I sort of picture it, here's how I sort of picture it, why this works, is like this. Let me draw for you my male world. And I'm going to draw it in sort of a roughly, this is very rough, but a roughly proportional way. So hopefully you could see that that's about, this is like 3 times the size of this, right? So this is 75%, this is 25%, right? So that's my females, this is my males, right? And I know that the probability of desktop given male is 33%. So now what I want to do is I want to divide this thing up into thirds, right? And I want 33% of that 75%. Well, in order to get that, I just multiply, right? I just multiply 75 times a third, right? And then I get whatever that actual area is. And that area is indeed 25%. It's 1/3 of 0.75. And that actually works for all of these things. For instance, here we have, 2/3, right, of 75. And that's really going to be this other section. And so in order to get that, I just take 2/3 of 75. And if you remember back in the day, this is, if you just think about it, that's like taking 2/3 of 75. That's multiplying, right? So that gives us sort of the raw value for that, and that's 50%. Right? And so let's see if that works with this one. So this is 80%, right? 80% of 25. So here we want, this much of 25%. What is the sort of raw value of that? Well, here what you would do is just multiply 80% times 25%, and we get 20%. So this section here is 20%, and then it makes sense that that is 0.05%, right? And so here we see that in order to find this probability, all we need to do is multiply these two probabilities together, right? So let's write that out. So the probability of D and M, desktop and male, is given by multiplying this proportion of this space, right? So this is like the total space, and you multiply it by this proportion. So the probability of D given M times the probability of M, of male. And if we want to generalize this so that it's not just for males and desktops, we might just write it in terms of, A and B equals the probability of A given B, right, times the probability of B, right? And really, my use of A and B is arbitrary. I could put X and Y or B and Z or whatever I want, right? And so it's just saying that you could generally follow this pattern. And in fact, you could also have the probability of B given A, right? So the proportion of the A space that's occupied by B given the entire A space times the probability of A. So, so this is sort of the generalized form of this part, right? And so now we know that there is a mathematical relationship between conditional probability, right here, and the and probability, right? And so if we really wanted to get down to it, what we could see is that, well, what is the very, very definition of conditional probability? Because we're defining conditional probability. Well, if we take this rule of probability of A and B equals the proportion of A, knowing that B, out of the B space, times the whole proportion of B. Well, we could rewrite this so that instead we solve for conditional probability. So that would be probability of A given B equals, so I want to isolate this, I just divide both sides by probability of B, equals the probability of A and B all over the probability of B. And in fact, that will give us conditional probability every time. The probability that both of these are true over the probability of just B being true. All right, so here's our definition of conditional probability, mathematical definition. Ta-da! But it's all stuff that's